On a cold January evening in 1683, 3 distinguished scientists were dining in London after a meeting of the Royal Society, when the conversation turned to the movements of celestial bodies. It was an unusual meeting between 3 of Europe's most brilliant scientific minds, Christopher Wren, Robert Hooke, and Edmond Halley, and one that would change the course of history. It would result in the publication of one of mathematics' most important works, and lead to Halley correctly recognizing that the comet he saw in 1682 was the same one that had been seen by others in 1456, 1531, and 1607. It's the comet that bears his name. Halley's comet has long had a hold on our imaginations. It returns to our skies roughly every 76 years, marking some of history's most remarkable and terrible events. In the 5th century, Halley's comet crossed the sky as Attila the Hun invaded Roman-controlled France, sparking the collapse of the Roman Empire. In 1066, it coincided with the Battle of Hastings and was seen as a good omen by the new king, William the Conqueror, who called it a wonderful sign from heaven. It wasn't a great omen for the defeated king Harold II, who died at the battle after being struck by an arrow in the eye, effectively ending Anglo-Saxon rule in England. In 1222, it was even more world-changing. One warlord is said to have considered the comet his own personal star, and its westward trajectory inspired him to head west, launching an invasion of Europe that would leave millions dead. His name was Genghis Khan. Each appearance of the comet in our celestial neighborhood found the world completely changed. A 76-year leap forward in our ability to document, analyze, and appreciate the astronomical object. Its most recent appearance in our solar system was in 1986, and humanity planned to get closer to Halley's comet than ever before by traveling into space. The Halley Armada was a series of spacecraft and probes that were sent into orbit to document the passage. And once again, Halley's comet would be a harbinger of doom. NASA's contribution to the Halley Armada, the Spartan 203 satellite, was scheduled to be launched on January 28, 1986. It was tucked into the hold of a space shuttle called Challenger. When Halley, Hooke, and Wren were dining in London and the conversation turned to the motions of celestial objects, the trio already knew that the planets were inclined to orbit the Sun in a particular kind of oval known as an ellipse. German astronomer Johannes Kepler had proposed 3 laws to describe this planetary motion. The problem was that his laws were derived from observation. They had no theoretical basis. Kepler's laws seemed to hold true, but no one knew why. Christopher Wren suggested a friendly wager, 40 shillings to whoever could provide a solution. Halley eagerly took up the challenge. A brilliant mathematician in his own right, Halley was convinced that the inverse square law lay at the heart of the problem, but he wasn't sure exactly how. Luckily, he knew someone who could help. A professor of mathematics at Cambridge and a man whose name you might recognize, Isaac Newton. What Halley couldn't have known was just what far-reaching consequences his meeting with Newton would have. Newton was a decidedly odd figure. Brilliant beyond measure, but solitary, joyless, irritable, and famously distracted. As a student, frustrated by the limitations of conventional mathematics, he invented an entirely new form, the calculus, but then told nobody about it for 27 years. Halley's meeting with Newton is perhaps one of the most influential in all of science. And thanks to mathematician Abraham de Moivre, who was a friend of both Halley and Newton, we have an account of what happened at that meeting. In 1684, Dr. Halley came to visit him in Cambridge. After they had been some time together, the doctor asked him what he thought the curve would be that would be described by the planets, supposing the force of attraction towards the Sun to be reciprocal to the square of their distance from it. Sir Isaac replied immediately, that it would be an ellipse. The doctor, struck with joy and amazement, asked how he knew it. "Why," saith he, "I have calculated it." Whereupon Dr. Halley asked him for his calculation without any farther delay. Sir Isaac looked among his papers, but could not find it. But he promised to renew it and then to send it to him. Halley couldn't believe what he just heard. Newton had casually solved a problem that had eluded mathematicians for centuries, then lost it. Newton agreed to redo the calculations and produce a paper. He did as promised, but then did much, much more. He retired for 2 years of intensive reflection and scribbling, and at length produced his masterwork, The Mathematical Principles of Natural Philosophy, better known as the Principia. Once in a while, only a few times in history, a human mind produces an observation so amazing and unexpected that people can't quite decide which is the more incredible, the fact itself or the capacity to think of it in the first place. The Principia was one of those moments. It made Newton instantly famous. It not only explained mathematically the orbits of heavenly bodies, but it also identified the attractive force that got them moving in the first place, gravity. Suddenly, every motion in the universe made sense. At Principia's heart were Newton's 3 laws of motion and his universal law of gravitation. Edmond Halley was pivotal in making the Principia a reality. He was the inspiration, the critic, the backer, editor, and publisher, and in his own book, A Synopsis of the Astronomy of Comets, published in 1705, he used Newton's new laws to calculate the gravitational effects of Jupiter and Saturn on cometary orbits. Having compiled a list of 24 comet observations, he calculated that the orbit of one particular comet that had appeared in 1682 was nearly the same as that of 2 other comets that had appeared in 1531 and 1607. Halley concluded that all 3 comets were in fact the same object, returning roughly every 76 years. He had found the comet that today bears his name, although it didn't become Halley's comet until 1758, some 16 years after his death. The passage of Halley's comet across the sky has been well documented in writing, in drawings, paintings, and tapestries, but 1910 was humanity's first opportunity to use some innovative, new technology to document the comet's passage, resulting in the first stereoscopic study which revealed important details about the object's composition and the first photographs of Halley's comet. But it all proved to be somewhat disappointing. The light pollution and smoke from industrial cities robbed the comet of its glory. So when the comet returned in 1986, we were determined to make the most of it. Humanity had moved on. The Industrial Revolution had given way to the space age, and we were in a position to break free of the shackles of gravity and make observations of the comet from space. Countries around the world planned to send spacecraft and probes into orbit to gather data on the passing comet. The Soviets launched the probes Vega 1 and 2, and the European Space Agency deployed a probe called Giotto, which captured these spectacular photographs of the comet's nucleus. Not to be outdone, NASA planned to launch Spartan 203, an astronomy satellite that would have studied ultraviolet light from the tail of Halley's comet. And what's more, NASA had a civilian join the crew, a teacher who would present a lesson from space demonstrating Newton's laws of motion. Unfortunately, the crew and the Spartan 203 satellite launched on the morning of Tuesday the 28th of January, on board NASA's Space Shuttle Challenger.
And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
73 seconds later, tragedy struck. There were no survivors.
I regret that I have to report that based on very preliminary searches of the ocean where the Challenger impacted this morning, these searches have not revealed any evidence that the crew of Challenger survived.
Aerospace engineer Alan MacDonald was concerned about the weather. A cold snap had descended on the southeastern United States, and the mercury had plunged below freezing in central Florida. MacDonald managed the solid rocket booster project for NASA contractor Morton Thiokol. He was at the Kennedy Space Center in Florida ahead of the Challenger launch. His role was to either approve or abort the shuttle launch based on issues that might arise related to the solid rocket boosters. One of MacDonald's colleagues, Bob Ebling, called MacDonald from Thiokol's headquarters in Utah. These were record low temperatures for Florida, and Ebling and the engineers back at HQ were concerned about the performance of the O-rings in the solid rocket boosters, or SRBs. The SRBs were manufactured in Utah, and due to their massive size, they were broken into segments so they could be transported to Kennedy Space Center and reassembled. The SRBs were then attached to a massive external fuel tank, and finally, the space shuttle itself was attached and readied for launch. The SRBs experienced immense heat and pressure during launch, and it was vital that the segments were securely fitted and sealed to withstand these forces. These field joints were sealed with a pair of large rubber O-rings, the first being the primary seal with a second backup O-ring. The Morton Thiokol engineers were worried that the low overnight temperatures might impact the O-rings' flexibility and their ability to create an effective seal. There was evidence that cold weather did affect the O-rings. Like the space shuttle itself, the SRBs were designed to be reused. After each successful launch, the SRBs were recovered and carefully examined. And on multiple occasions, evidence of O-ring damage was found. 1 year earlier, the Space Shuttle Discovery had launched from Cape Canaveral. After recovering the SRBs, the O-rings were examined. They were damaged. The primary ring hadn't maintained a seal. At that time, the launch was the coldest yet, at about 12 degrees Celsius. Alan MacDonald phoned officials at NASA to inform them that the cold weather may impact the O-rings and jeopardize the launch. He was also concerned about ice forming on the launch pad that could damage the shuttle at launch. It was decided that a conference call would be set up between engineers and management from Morton Thiokol and NASA. Some of the Morton Thiokol team were at Kennedy Space Center, others were back at HQ in Utah. The NASA contingent were at Marshall Space Flight Center in Alabama. The call didn't go well for the Thiokol engineers. Roger Beaujolais presented the data, much of it handwritten, showing that the O-rings might fail in cold weather conditions, and the engineers recommended the launch be aborted. At this point, Challenger's launch had already been postponed 3 times. NASA's manager of the Space Shuttle booster program, Larry Malloy, didn't hide his disdain. "My God, Thiokol," he said. "When do you want me to launch? Next April?" George Hardy, NASA's Deputy Director of Science and Engineering, said, "I am appalled by your recommendation." At this point, it's probably a good idea to take a very brief look at the history of the Space Shuttle program. It began in 1969, when then President Nixon brought together a panel of experts to decide the nation's space exploration goals in the wake of the Apollo program. The group produced a report called the Post-Apollo Space Program: Directions for the Future. And in 1972, Nixon directed NASA to begin development of the Space Shuttle. The first Space Shuttle, Columbia, was delivered to Kennedy Space Center in 1979, and the first ever launch took place in April of 1981. The Space Shuttle was supposed to be a reusable space truck, a profit-making, economical spacecraft intended to make spaceflight easy and accessible. NASA planned and secured budget for up to 50 launches per year. By 1986, they hadn't even got close to that number. The public was also losing interest in space. As the number of launches increased, the novelty decreased. NASA was no longer front-page news. The massively expensive Space Shuttle program was paid for by taxpayers, and the public's interest and goodwill were vital to NASA's funding. In August of 1984, President Ronald Reagan announced the Teacher in Space project. designed as a showcase for the resurgent space program and to promote interest in mathematics, science, and space exploration. Skeptics believed it was a gimmick, an attempt to bolster Reagan's re-election campaign and get NASA back in the headlines. In 1985, NASA selected Christa McAuliffe to be the first teacher in space, with Barbara Morgan as her backup. President Ronald Reagan was due to mention McAuliffe and the Teacher in Space project in his State of the Union address on the night of January 28th. If the launch was delayed, NASA would miss out on another big public mention. If the agency was going to justify continued spending on the program, Challenger had to launch on time. On the night of the conference call, all this pressure on the Shuttle program to deliver on its promise and to launch Challenger in time for the State of the Union address fell on the shoulders of NASA manager Larry Malloy. On the conference call, after Malloy and other NASA officials voiced their disgust at Alan McDonald's suggestion to delay the launch again, Thiokol managers asked for a short break to discuss the issue in private. Thiokol's Vice President Joe Kilminster in Utah told the engineers that if they could not say for certain that the O-rings would fail, the decision would be made by management. Kilminster then polled Thiokol management officials and got a unanimous decision to approve the launch. Engineer Roger Beaujolais would later recall, "There was never one comment in favor by any engineer before or after. When it became a management decision, I was not even asked to participate. I did not agree, I was never asked or polled. It was clearly a management decision. There was no point in me doing anything further. I really did all I could to stop the launch." NASA insisted that the Thiokol recommendation to launch be put in writing. Alan McDonald refused to sign it. Overnight temperatures had fallen to -4 degrees Celsius, and ice had formed on the launch structure. The launch was delayed by an hour to allow the ice to melt. Challenger was cleared to launch at 11:38 a.m. The temperature was just above freezing point, at 2 degrees Celsius. Hundreds of spectators, including the family members of the 7 astronauts on board Challenger, gathered at Cape Canaveral. Thousands of classrooms across the United States tuned in to watch Christa McAuliffe become the first teacher in space. Instead, they saw a national disaster unfold live on television. 73 seconds into the launch, disaster struck. There was shock and confusion in mission control and in the crowd of spectators. But soon, the horror of what has happened becomes clear. On reviewing the launch footage, the appearance of an unusual plume suggested that an issue with the solid rocket boosters could be behind the tragedy. The public are shocked and horrified. President Reagan quickly moves to form a presidential commission tasked with finding out what caused the disaster. President Reagan appoints former Secretary of State William Rogers to helm the commission. It's later reported that Reagan told William Rogers, "Whatever you do, don't embarrass NASA." Rogers was joined on the panel by 12 experts, including Sally Ride, a NASA astronaut, Major General Donald Kutina, who oversaw the Space Shuttle program on behalf of the Department of Defense, and Nobel Prize-winning physicist Richard Feynman. Ride, Kutina, and Feynman would play a vital role in uncovering the truth of what happened to Challenger. During media appearances in the aftermath of the Challenger explosion and in the opening few days of public testimony at the Rogers Commission, it became clear that NASA was downplaying the fact that the O-rings were a known issue on the SRBs. On one appearance before the commission, NASA manager Judd Lovingood said this about damage to the O-rings.
We have seen some evidence of what we call blow by those seals, some erosion of those seals. The primary seal. We've never seen any erosion of the secondary seal.
Richard Cook, a NASA budget analyst, saw the televised commission testimonies and couldn't stay silent. He leaked documents to the New York Times clearly showing that NASA had known about issues with the O-rings, and there had been instances, such as the launch of Discovery in January 1985 and Challenger in April of that year, where examination of the SRBs found that the primary O-ring had been destroyed and the second had been partially eaten away. When the New York Times ran the story, the Presidential Commission held a closed session and Larry Malloy returned to explain the leak and give more information about exactly what happened on the conference call the day before the Challenger disaster. Malloy simply said that Thiokol had some concerns but approved the launch. He neglected to say that the approval came only after Thiokol managers, under intense pressure from NASA officials, overruled their engineers. This particular session of the committee was held behind closed doors. Unlike other sessions, it wasn't televised, but Morton Thiokol engineer Alan MacDonald was there, sitting in what he called the cheap seats. MacDonald would later recall, "I was sitting there thinking, that's about as deceiving as anything I ever heard. So I raised my hand. I said, I think this Presidential Commission should know that Morton Thiokol was so concerned we recommended not launching below 53 degrees Fahrenheit. And we put that in writing and sent that to NASA. I'll never forget, Chairman Rogers said, will you please come down here on the floor and repeat what I think I heard?" From that moment on, the focus of the Commission's investigation shifted to the booster rocket O-rings, the efforts of MacDonald and his colleagues to stop the launch, and the failure of NASA officials to listen. William Rogers' attempts to shield NASA from embarrassment was in tatters, and there was worse to come. There was one more whistleblower, an astronaut, who had flown on Challenger. Sally Ride was an astronaut and physicist. She joined NASA in 1978 and in 1983 became the first American woman to fly in space. In the early stages of the Rogers Commission, Donald Kutina and Sally Ride were walking together. Kutina recalled, "She was on my right-hand side and was looking straight ahead. She opened up her notebook and with her left hand, still looking straight ahead, gave me a piece of paper. Didn't say a single word. I look at the piece of paper, it's a NASA document. It's got 2 columns on it. The first column is temperature. The second column is resiliency of O-rings as a function of temperature. It shows that they get stiff when it gets cold. Sally and I were really good buddies. She figured she could trust me to give me that piece of paper and not implicate her or the people at NASA who gave it to her, because they could all get fired." Donald Kutina had a dilemma: how to introduce the evidence without implicating Sally Ride and other NASA insiders. He struck on an idea. He'd give the information to an outsider. Richard Feynman was a brilliant physicist. He was an anti-establishment figure and an unusual choice for the Rogers Commission, but the perfect choice for Donald Kutina's plan. Kutina and Feynman had struck up an unlikely friendship, and one evening Kutina invited Feynman to his house for dinner. After dinner, they went to his garage. Kutina recalled, "I have a 1973 Opel GT, a really cute car. We went out there to the garage and I'm bragging about the car, but he could care less about cars. I had taken the carburetor out and Feynman said, 'What's this?' And I said, 'Oh, just a carburetor. I'm cleaning it.' Then I said, 'Professor, these carburetors have O-rings in them, and when it gets cold, they leak. Do you suppose that has anything to do with our situation?' The following day, Richard Feynman conducted a simple experiment that demonstrated the inevitability of the Challenger disaster.
Oh, I took the stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem."
The Rogers Commission published its findings on June 9, 1986. The Commission found that the immediate cause of the Challenger accident was a failure in the O-rings sealing the field joint on the right solid rocket booster. The Commission ultimately found the root cause of the accident as a serious flaw in the decision-making process leading up to the launch. 7 lives could have been saved if concerns about the O-rings had reached the right people, or if Thiokol had worried more about safety than satisfying its major customer. The Commission also found that the White House didn't pressure NASA to launch Challenger in time for Reagan's State of the Union message, but the White House declined to release records to a Senate inquiry that was investigating those rumors. Whistleblower Alan MacDonald was treated as a traitor and pariah by NASA and his own company, but thanks in part to congressional pressure, he was given a new task: redesigning the SRB field joints. The Space Shuttle program was shut down for 2 years, and in September 1988, Space Shuttle Discovery successfully launched using Alan MacDonald's new design. There were a further 86 successful launches before another disaster effectively ended the Space Shuttle program for good. In 2003, the Space Shuttle Columbia disintegrated during re-entry due to damage to the wing caused during launch. All 7 of the crew members were killed. The investigation again found deep cultural problems at the heart of NASA. After the Columbia disaster, President George W. Bush announced the program would end after work on the International Space Station was complete. The Space Shuttle program never lived up to expectations. It was wildly expensive, with the average cost of a shuttle launch coming in at a mind-boggling $450 million, far more than NASA had predicted. The proposed launch schedules and turnaround times for the shuttle fleet were essentially fantasy. The fastest turnaround for any shuttle in the history of the program was 54 days, and after the Challenger disaster, the fastest turnaround was 88 days, a far cry from what NASA officials thought they could accomplish. And lastly, the loss of Challenger and later Columbia forever dispelled the notion that spaceflight was routine. A total of 18 people have lost their lives on space missions. 14 of them were on the Space Shuttle. The 1986 passage of Halley's Comet was overshadowed by the tragedy of the Challenger disaster. Challenger crew never got to launch the Spartan Halley satellite, and teacher Krista McAuliffe never got to present her lesson demonstrating Newton's laws. It's incredible to think that since Halley identified the comet in 1682, it has only visited our celestial neighborhood on 3 other occasions. We're left wondering, when Halley's Comet returns for its 4th visit in 2061, what kind of world will be waiting for it? Thanks for watching, and if you haven't already, please hit the like button and consider subscribing to the channel. And if you want more outer space content, check out my video on the dinosaur extinction.